happy to be able to join and to be with you. So then now also to have this possibility to give this talk, which has, I mean, I'm working really, I'm chair of functional analysis, and some part of my work is maybe in abstract evolution equations. But of course, the focus of applications are partial differential equations. So I want to give some non-standard examples, or maybe, yeah, for some people, non-standard examples, but you should not be afraid if you don't know these systems, and we don't go into details too much, but I will explain a little bit. I will then recall some classical theory by Bresis and many others on gradient systems. And then I will slightly modify this classical theory, actually not too much, in order to show how we can apply this to the examples now I present here. Please, whenever you have questions, interrupt me at any time if I'm going too fast, or if you want to see something again, that I will be happy to say more also. So here's a complicated system. By the way, can you see my mouse, or actually something moving?
Yes, we can see.
Okay. So this is the so-called Bidomain problem on a domain omega in Rn. And here are two unknown functions, both defined on time and on space, omega. That are the two functions ui and ue. The origin of this problem comes from mathematical biology, or actually it's some tissue models, activity in the heart or in the brain. And really there are two potentials, electric potentials, given inside cells and outside cells. And across the membranes, there is some dynamics going on. But when you look from very far, when you do some homogenization, you can say that actually ui and ue are defined on the same domain. And this is an evolution equation here for the difference of the two potentials, so inside and outside, but here both on omega. And here is some elliptic operator in the first line in the middle, some elliptic operator which acts only on one of the potentials. Okay, and then there's also a semilinear lower order term. There's a function f defined on R2. It depends on two variables, and we take the derivative here with the first variable. And so it's a lower order term here. The first equation is an evolution equation. The second equation actually links two elliptic operators, one acting on ui and the other one on ue. And the sum of them should be 0. So please remember that both variables depend on time, but somehow here the second does not explicitly depend on time, the second equation. Okay, then there are some Neumann boundary conditions, not so important. And actually, this model is then also coupled. There's a third variable w here, and that's an ODE. So the above system is coupled with an ODE. But for us, without going into the modeling and so on, it is just important that there's an evolution equation coupled with the first line, with the second line, an elliptic equation. And yeah, so the model is quite old, goes back to the 60s. well, with maybe simpler models for the evolution of electric potentials in cells. But it has been recently be studied again from the point of view to show well-posedness here in certain functions. Yes? Is there some question?
No.
Maybe not?
No.
Okay. It has been studied recently to study well-posedness in certain function spaces, LP spaces, spaces of continuous functions, by, for example, Giga, Hieber, and Prüss in several articles. And when we forget the nonlinear terms, I mean the lower order terms, and when the elliptic operators are linear operators, then the system can be written in an abstract way as a coupled evolution equation and stationary equation of this form, where AI and AE are these elliptic operators. And in the papers of Giga, Hieber, and Prüss, they consider the case where all these operators are linear. And actually, this system can be rewritten as a Cauchy problem, where the operator A is given on the bottom here. It's somehow the harmonic mean of two elliptic operators. And although the two elliptic operators are local operators, the partial differential operators, the harmonic mean is in general a non-local operator. And what they did is studying this in detail and showing well-posedness in LP spaces. And once you have well-posedness for this linear problem, then you can solve the semi-linear problem with lower order terms by applying fixed point theorems. That's what they did. It then meant, when you apply these fixed point theorems, that they had to restrict on dimension and growth of the lower order terms. But of course, this is more or less standard then. But the difficult part is to show well-posedness of the linear problem. Actually, one has here analytic semigroups. Much earlier, in Hilbert space, just in L2, Colli, Franzone, and Savary and others viewed this problem as a degenerate Cauchy problem of the form here, so where B is not the identity operator and B, well, is in general even not injective. So, but then but A is also linear. They also consider the case where the operators are linear. And they developed a theory which is very much close to what I will present later. Yeah, there's a different motivation. That's the Dirichlet-to-Neumann operator or problem. That's an evolution equation of different type. So here you use the P Laplace operator, but you can take P equal to 2 and you have the Laplace operator inside a domain omega. But you see the second line that looks like a stationary problem, but actually there's an evolution on the boundary. So time derivative of u on the boundary plus Neumann derivative is equal to 0. And yeah, so this is also from the structure, some parabolic equation or some evolution equation on a boundary here in this example, coupled with an elliptic equation. Also, I will not go into details where this comes from, but it has also applications in even in medicine, but that's not important here. this problem was also written as a Cauchy problem by Arendt and ter Elst in 2012 and in several papers actually, where they developed a theory how to deal with such kind of problems. Well, where you have this coupling of a parabolic equation and an elliptic equation. And I will also come to this later. Well, and here is a more classical problem, diffusion equation in omega. And what I want to show, all these problems have in some sense a similar structure, a structure of gradient system. And that's an old theory. And sometimes I have the impression it's a little bit forgotten theory, or, well, in some sense also extended theory by the theory of gradient systems in metric spaces. But I want to recall some old results here. So the abstract setting is that we have a Hilbert space, and on this Hilbert space we have a function. It's real valued, but it can also take the value plus infinity, which is semi-convex and lower semi-continuous. Semi-convex is written here in the middle. So when I add norm square for some omega, omega is in R, then we should get a convex function. In many old texts, omega is equal to 0. So we really treat with convex functions and lower semi-continuous. And we define the effective domain of such a function as those elements where the energy is really real valued, finite valued. And for such energies, I call them energies, because in many examples, they really play a role of energy. We define the subgradient, and the subgradient is a relation on the Hilbert space. It's really a general relation of pairs, a set of pairs where the first component has finite energy, U is in the effective domain of E, and some directional derivatives are estimated from below by linear functions. So that's why it's called subgradient. Here, somehow the derivative is estimated from below by a linear function. It's not equal to a linear function. And this linear function is given by an F and the inner product, H. And when we have such a relation, we also write the subgradient at a point U is the set of all F such that UF is in the subgradient. So it's a set valued function also, but really it's a relation. And here is an example. So classical example. So the Hilbert space is L2, and we take P, some number between 1 and infinity, and we define somehow this non-standard Sobolev space of all functions in L2 with gradient in LP. And the energy is somehow the Dirichlet energy, but well, here with P. So the integral of gradient U to the power P, if U is in the Sobolev space and plus infinity else. Here the effective domain is a linear subspace of L2. For this energy is convex, lower semi-continuous. The effective domain is even dense in L2. And the subgradient actually can be seen as a single valued operator. It's in general a relation, but here it's a single valued operator. It's a realization of the P-Laplace operator with Neumann boundary conditions. We can make this a little bit more complicated. We can also add such an integral in order to produce lower order terms. So here's the integral with f of u added, and then the subgradient is the P-Laplace operator with Neumann boundary conditions plus this lower order term. And in order to make the integral convergent, here f prime is Lipschitz continuous, but that's not important. Also, this operator is a subgradient. And okay, we can also add obstacles, but that's not important. What I want to study is an evolution equation here in the middle. It's not actually not an equation, it's a differential inclusion. So we are looking for functions u, depending on time, it's on an interval 0t or on r plus, with values in h, which satisfy this differential inclusion. That means u of t, also the subgradient at u of t is non-empty and it contains minus the derivative. Or 0 contains this set shifted by u dot. And this is one of the, I think, nicest results in maybe in nonlinear evolution equations. I mean, simple equations, gradient systems, that under very few properties, so here the energy is proper, semi-convex and lower semi-continuous. This can be, in many examples, can be checked very easily. Then you have already existence and uniqueness of solutions for every initial value u0 in the effective domain. You get, so under these very few properties, you get solutions. And the solution is even very nice. It's an h1 in time. So the derivative exists almost everywhere on the weak sense. And yeah, and this differential inclusion is really satisfied almost everywhere. So it's not a weak solution. I would call this a strong solution. And what is important also, the energy along the solution. So when I compose E with a solution, this gives a differentiable function. And the time derivative is negative. So the energy is decreasing along solutions. And here appears actually the norm, or the absolute value, but the norm of subgradient, which is actually a set. So this is defined here in the last line. So very few assumptions, and somehow the best possible result one can have. Existence, uniqueness, and even regularity, a strong regularity. You can find this result already in the book by Bressis from 73, and maybe you know this book and this theory, I don't know. Yeah, but it belongs to the French school, and besides the book by Lyons, or the books by Lyons, Jacques Lyons, I think this is one of the important first results in this type of evolution equations. Actually, this energy equality can also be taken in order to get solutions, to define solutions. So actually, if a function in H1 satisfies the energy equality, then U is a solution. This is just a side order remark. This observation by De Giorgi has been used in order to define a theory of gradient systems in metric spaces, not in Hilbert spaces, but in metric spaces. And this is a more recent theory, well, with a very early book written by Ambrosio Cigli and Savary. The theorem by Précis also implies this well-postness that we have a nonlinear semigroup on the effective domain. And this nonlinear semigroup is Lipschitz continuous. And the orbits of the semigroup or dynamical system are actually the solution of the abstract gradient system. And when you have this Lipschitz continuity, then you see that you can extend the semigroup in a unique way to the closure of the effective domain. So actually initial values can also be taken in the closure of the effective domain. And you have a regularizing effect here. Actually the solutions, even if you start only in the closure, the solutions will immediately land for positive times in the effective domain. Also, this is in the book by Précis. Yeah, and once you have well-postness, you would like to study properties of solutions like regularity or approximation, maximum principle, or comparison principles, or asymptotic properties like convergence to equilibrium. You would like to study this just by analyzing the energy. So express properties of the semigroup in terms of E. And I mean, there would be a lot of things to tell about each part, but I will just say something quickly about maximum and comparison principles. If the Hilbert space is an L2 space, then we can say that a semigroup is positive if initial values which are positive lead to positive solutions. So the solution remains positive. Or the semigroup leaves the positive cone of L2 invariant. There are already quite early results by Précis and also Passy, actually. But you can find these results in the book again, that one can characterize positivity just by showing an inequality that if the energy at positive part of some element is smaller than the energy of U, then the semigroup is positive. And actually this is if and only if. From a more abstract way, positivity can be seen as an invariance of convex sets. So the cone of L2 is convex and closed. And actually, one can also characterize that a set C is invariant under a semigroup. That's assertion 1, and all the following assertions are equivalent. This is equivalent by checking an inequality 2, and here PC is the orthogonal projection onto the convex set C, closed convex set. And actually for the positive cone, the orthogonal projection is just taking the positive part. So it's a special case, the theorem which we had before of this more general theorem. One can also formulate this in a different way by saying that the indicator function of this convex set, which is 0 on the convex set and plus infinity outside, is a Lyapunov function, so it's decreasing along solutions. That's written in assertion 4. But one should say that in this old characterization of invariance, the energy is convex and not semi-convex, which would be a little bit more general. And there's a recent generalization of this. Actually, when you have proper semi-convex, lower semi-continuous functions, E and psi, then both of these generate semigroups. And there's a duality theorem that one function is a Lyapunov function for the semigroup generated by the other function, if and only if, I mean, you can invert the two. That's a quite recent result, and actually there are even more general versions of this theorem, but this of course implies these old results by Précis and Passy and applies also to more general situations. Maybe diffusion equations with lower order terms. Yeah, and in this way, I mean, just by considering, I mean, diagonal semigroup on a product space, you can also characterize that a semigroup is order preserving, and this means actually that a comparison principle holds. That's a little bit more general, or more, not more general, but a stronger property in general than positivity, that you also have a comparison principle. And here's a characterization. We will not use this too much, but just to say, to give a flavor that by properties of the energy, we can characterize properties of the semigroup and of solutions. And when we say, okay, when we apply this, for example, to the energy of the Plie-Laplace operator, that was one of the first examples, actually this semigroup is positive order preserving and L-infinity contractive, and such semigroups or energies of this type I would call Dirichlet forms, nonlinear Dirichlet forms. There's a whole theory of Dirichlet forms in the case of linear operators, linear elliptic operators, but here one can also characterize them in the nonlinear setting. Okay. And yeah, here's the definition of Dirichlet form. That's just characterized by the order preserving. The semigroup should be order preserving and L-infinity contractive. Let's go to an application where we have a Dirichlet form. Actually, you don't only have a semigroup on L2 space, but on all LQ spaces. That's done by extrapolation. L-infinity contractivity is actually equivalent to L1 contractivity, and then you interpolate between L1 and L-infinity. So you get here well-postness also in different spaces than L2 by this L2 theory. Yeah. Now I should come to change the setting a little bit, this classical setting. Here is again the classical setting, which by Précis and others, actually also the gradients, subgradients are considered earlier in the 60s also. So we consider semi-convex lower semi-continuous functions, but our energy is defined on a different space. Please note here, so H is our Hilbert space, and now the energy is defined on a different space, V, linear space. Before this was H. And the subgradient is a relation on H. Now, if E is not defined on H, somehow this definition doesn't really make sense. And one has to change it a little bit, but one can change it in a reasonable way. Still, the subgradient is a relation on H, but now V is a Banach space, which, and there's a linear and continuous operator from V to H. For all those who know Gelfand triples, there's always this embedding of V into H, but the J here is not injective and doesn't have dense range. All this is not necessary. It's just a linear and continuous operator. And we assume that E is J-convex, semi-convex, so I will explain, and lower semi-continuous on the Banach space V. And we change the definition of subgradient. Although the energy is defined on V, the subgradient is an operator on H, so still couples pairs UF in H, but U has a pre-image U hat in the effective domain of E. So here it has a pre-image, and the directional derivative of E at point U hat can be estimated from below by a linear function, but now it's a linear function, yes, on V, but here's a J also appearing on the right-hand side. So, and we call this, there is elliptic, but that's somehow semi-convexity means just that this shifted functional energy is convex. And now we also assume that it's not only convex, but also lower semi-continuous and coercive in the sense that sublevels are relatively weakly compact. That's just some technical thing. And we have not defined new objects in this way. That's this theorem, which says if E is an energy on this Banach space V, semi-convex and J-elliptic, and we define the subgradient on H, this J subgradient, then actually this is already a subgradient for some energy on H. That's important. We have not defined something new, but maybe in applications the energy E is known, while this energy on the Hilbert space H might be difficult to describe. But it exists. Therefore, by this thing that we have not defined something new, okay, I can solve the corresponding subgradient, the gradient system. But here's an example. I take again the energy of the P-Laplace operator, but on this Sobolev space, which we had before. So the space of all L2 functions with gradient in LP, that's our Banach space. And this Banach space on omega, of functions on omega, is not embedded into L2 of omega, but now into L2 of the boundary by the trace map. So, and the trace map, of course, is not injective because functions which vanish on the boundary, test functions, are mapped to 0. So, but the energy is some well-known energy, and the J is a little bit non-standard. And one can show that the subgradient on L2 of the boundary, that's a realization of the Dirichlet-to-Neumann operator, even of this nonlinear P Dirichlet-to-Neumann operator. And therefore, the system here is a gradient system. But I don't describe the energy on L2 of the boundary, but I use the more classical theory, energy defined inside of omega, or on functions which are defined on omega. So this is a gradient system, and it's well posed. And actually, one can show more for this energy. The form here is actually a Dirichlet form. So the semigroup, the nonlinear semigroup generated on L2 of the boundary is order preserving and L infinity contractive. It's L1 contractive. And actually you get semigroups on all LQ spaces on the boundary. You have well-posedness also on these spaces, not only on L2. And you get everywhere contraction semigroups. And you have a comparison principle. This is very easy because one already knows the comparison principle for the energy of the P Laplace operator, and the trace map is positive, and then this transfers to this semigroup. So it's somehow elegant to solve this problem on the boundary. And now again, this more complicated Bidomain problem. Also, this is a gradient system. Sorry, here is the energy. So there are actually two evolution equations in this Bidomain problem. The first line and this ODE below. It's an ODE, but also W depends on T and on X, but it's an ODE. So it's not surprising to take as H product space L2 with L2, but my Banach space V is the Cartesian product of three Banach spaces. I haven't said nothing about the coefficients Q, but let's say you have Qi and Qe, the coefficients here are such that this energy is well defined on the Sobolev spaces W1 to P. So this is close to something which is P Laplace operator, and you take the corresponding energies of these elliptic operators. So one term for the variable ui, one term for the variable ue, and for this semilinear term, you have this function f. And now you have a mapping from this product of three spaces into product of two spaces. Actually, there's a mistake, a misprint here. This is L2 of omega in the Bidomain problem. So the space H appears on the right here. And you just take a triple is mapped to a couple and just take ui minus ue. And actually, it's very easy to check that the subgradient on the space H for this energy, which is somehow also not surprising energy for this problem, when you think about it, actually the subgradient is really the Bidomain operator. So everything, This part here is described by this operator. Everything, all lines, also the Neumann boundary conditions, is included into the subgradient, and this is really a gradient system on the product space L2 with L2, and you can now solve for every initial value. You get a solution. Just by this idea, but actually it's a classical gradient system, but I don't know the energy on the space H. I rather use this natural energy on the space V. Well, so as a consequence of the well-postedness, you get this theorem that you have uniqueness of solutions. You have even here solutions not in the space H, but you have solutions in the space V, in this energy space. And you have a certain kind of regularity. One should say that the Bidomain problem, the real Bidomain problem, the semilinear term is not so simple. It's not of the form one partial derivative and another partial derivative, but actually you should replace these two partial derivatives by these nonlinearities below, and actually these nonlinearities below on the right, they are not of this gradient type, but they are almost of gradient type up to one linear term. So maybe if I take out, let me just see, if I take out, I think this term here, this constant, then it is a gradient, but without this, just let me see, where's the problem? I think the signs here are not good. Here's a plus W and minus U, so this is not really a gradient from a function. But it can be changed by just adding a lower order linear term, and this doesn't affect solvability, so you can really solve the Fitzhugh-Nagumo model. So this nonlinearity of order 3 leads to a double well potential behind this, and that's semi-convex. It's not convex, but it's semi-convex. Yeah, one can also solve many other equations of this type where you have, so here's another problem on surfaces. I will not go into detail. All this is this journey started with an old internet seminar, but I'm actually working still in this area and trying to write a book, which will be published in, I don't know, today plus epsilon, and epsilon is a positive number, can also be infinity. Therefore, thank you very much for your attention. And of course, I'm open for questions.